Continuing with curve sketching, we're going to look at some more examples. In this particular video, we're going to focus on the function f of x equal x minus 2 sine x, restricted to the interval from 0 to 3 pi. In fact, we've already looked at this particular function when we were investigating intervals of increase and decrease. If we start with the domain, then x is defined, of course, on the real line, and sine x is also defined for every x. So the function x minus 2 sine x by itself would have the domain the real line, and we look at the restriction to 0, 3 pi. There's no problem of definition. In particular, there's no vertical asymptote for this function. We cannot really talk about horizontal asymptote or slant asymptote at all here, since we are looking at the restriction to the function on a closed interval, and vertical and slant asymptotes are about the behavior of the function when x goes to either positive or negative infinity. So we turn to intervals of increase and decrease. That depends on the first derivative. First derivative here is 1 minus 2 cosine x, and so we want to know when f prime is positive. It's positive when cosine x is less than 1/2, and this is a question that we looked at in the previous module. If we want to find out where the derivative changes sign, we can look at the behavior of cosine x on the unit trig circle. There is 1/2. Remember that if you pick a point on the trig circle, the cosine of the corresponding angle is a projection on the x-axis. So at pi over 3 in particular, the cosine is going to be 1/2. Similarly at negative pi over 3. For the angle we're interested in, we start at angle 0, and you see that if the angle is between 0 and pi over 3, then the projection on the x-axis is greater than 1/2. Since the condition for f prime to be positive is that the cosine is less than 1/2, we find that the derivative is negative from 0 to pi over 3. Then, if we continue to increase the angle from pi over 3 all the way to 5 pi over 3, you see that the projection on the x-axis is less than 1/2, and therefore the derivative is positive. From 5 pi over 3 all the way to 7 pi over 3, we're again on the side where the cosine is going to be greater than 1/2, and therefore the derivative is negative. And from 7 pi over 3 to 3 pi, we are again on the side where the cosine is less than 1/2, and therefore the derivative is positive. In terms of intervals of increase and decrease, that means that the function is decreasing from 0 to pi over 3, and again from 5 pi over 3 to 7 pi over 3, and is increasing from pi over 3 to 5 pi over 3, and again increasing from 7 pi over 3 to 3 pi. That gives us a local minimum at pi over 3, a local maximum at 5 pi over 3, and a second local minimum at 7 pi over 3. To get the second coordinates, we simply plug these values in the original function. So, putting these values inside my chart, this local extrema, here's what I get. And I add to it also the values at the endpoints because we are on a closed interval. So the value of the function at 0 is 0, and at 3 pi it's 3 pi. So we have the intervals of increase and decrease and the local extrema, but if we want to sketch a graph, we also need something about concavity and inflection points. That depends on the second derivative. In this case, derivative of cosine is negative sine, and therefore derivative of 1 minus 2 cosine x is going to be 2 sine x. So it's about when sine x is positive or negative. Again, we can take a look on the trig circle. If x is an angle from 0 all the way to pi, the sine, which is the projection on the y-axis corresponding to the angle, is positive, and therefore the second derivative is positive from 0 to pi. From pi to 2 pi, we describe the lower half circle where the sign is negative, so we get a negative second derivative. And from 2 pi to 3 pi, we describe again the upper half circle where the sign is positive, so the second derivative is positive again. The interpretation in terms of concavity for the graph of the function f is that it's concave up on the interval 0 pi, concave down on the interval pi 2 pi, and concave up again on the interval 2 pi 3 pi. So now let's try to sketch the graph from all that. Note that we have two changes of concavity at points on the graph, namely at x equal pi and x equal 2 pi. If we plug these values inside the function, at pi we get pi, at 2 pi we get 2 pi. So these two inflection points gives us two more intersection points with the diagonal y equal x. Okay, let's sketch the graph now. Normally we should start with asymptotes, but in this particular case it's not relevant. And you see that we have several points of the graph that are also on the line y equal x. So just to help me do the picture, I will start by drawing this line y equal x, which I will remove at the end. Points of the graph that are on y equal x are the endpoints 0, 0 and 3 pi 3 pi, and also the two inflection points pi pi and 2 pi 2 pi. The other important points that we have to plot are local extrema. So we have a local minimum at pi over 3, and there we have an horizontal tangent, a local maximum at 5 pi over 3, with again an horizontal tangent, and a second local minimum at 7 pi over 3. Here I have given both coordinates for each one of these local extrema. Then we're going to try to connect all these points in a smooth fashion using the information we have in the chart. So if I look at the first interval from 0 to pi over 3, the function is decreasing and is concave up. So I join my point 0, 0 and my first local minimum with an arc that is smooth, decreasing and concave up. Moving to the next interval from pi over 3 to pi, the function is now increasing but still concave up until I reach the first inflection point. So again, I join my first local minimum to the first inflection point in an increasing and concave up fashion, so I get something like that. Moving to the next interval, the function is still increasing, but is now concave down because I went through an inflection point where I have a change in concavity. So again, I connect my inflection point to the next local extremum in an increasing concave down fashion, so something like that. Moving to the next interval from 5 pi over 3 to 2 pi, I see that the function is decreasing and still concave down, so I connect my local maximum to the next inflection point with a smooth arc that is decreasing and concave down. Then on the next interval from 2 pi to 7 pi over 3, the function is still decreasing, but now the concavity changes to concave up again because I'm going through an inflection point. So I connect the second inflection point to the second local minimum with a smooth arc that is decreasing and concave up. And finally, on the last interval from 7 pi over 3 to 3 pi, the function is increasing and concave up, so I connect my local minimum to the endpoint 3 pi 3 pi with a smooth arc that is increasing and concave up. And here is my graph. Now let's turn to the next video to see more examples.